Alright, buddy. Here we go. Alright, man. Making a video just for you to post on the World Wide Web. It's kind of weird, isn't it? But it's actually really cool, too. Alright, Newton's method. Okay, let me give you a quick big picture, buddy. Big picture, Newton's method is to find zeros of functions. Because a whole lot of functions we can find zeros of without this. Like if I said, here, find the zeros of this. Y equals x squared minus 1. Well, you go, oh, find the zeros. Let y equal 0 and solve for x. You could do that, right? X plus 1, x minus 1 equals 0, x equals negative 1, or x equals positive 1. That's no problem. But what if it's some real ugly, messy function that, like, you can't factor? 3x squared plus x plus 1. That's a real messy x, but anyway, you can't factor that. So if I set that equal to 0, I don't know how to solve that, but I got to know the zeros. The zeros are the most important points on functions, or at least one of them. And so we want to be able to find them. The other thing is, this Newton's method is how a lot of calculators are programmed to actually find the zeros when it does find the zeros for you. So it's good to know how to do that for that reason as well, if you ever go into, for people that go into programming or whatnot. But anyway, I erase these and we'll go back to show you why it is what it is. So let's look at a function. Set you up here. I've got my graph here. Darken it up a little bit. Okay, so suppose I've got my graph looks like this, and I've got a function. Let's say it goes like this. Oops, don't know what that is. That's all about. Okay, so say it looks like that, and I want to find the zeros. I want to follow the 0. I want to find this 0. Okay, what that is. Well, the way it works is you approximate the 0 first. You just look at the graph and guess something around it. So I'm going to make a guess. The first guess is, call it, say, x sub 1. And I'll keep blowing up on this so you can see it as we look at this. Okay, so there's my first guess. And now watch what happens here. Make this bigger. Okay, if I make this first guess x sub 1, that has coordinates x sub 1, f of x sub 1, right? And the whole principle behind this is that when you draw this tangent line, that tangent line, the root or the 0 for that tangent line is really close to the actual 0 here. Right? These two numbers right here and here, the distance between those two numbers right there is really? Did I just do that? Sorry. See, I'm a rookie. So say it does that. Okay, so the 0 that from this line is really close to the actual 0. So this is my first guess, x sub 1, and then this guy right here will be my second guess, or my second estimate, x sub 2. Okay, now watch what happens here. That's my second approximation. Then I draw a tangent line from my second approximation. I'm going to use green, and I do a tangent line. Now that's really going to be really close. Now I kind of made it messy because I messed up my drawing a little bit, sorry. But that's going to be really close to the actual 0. Okay, and every time I do that, that's going to hit the x-axis right here. That's going to be x3. So see, I've got x1 is my first approximation, my first 0. Draw a tangent line. there's x2. Then I draw a tangent line to it, get its 0. Then I draw, so that's x3. Then I would draw another tangent line here. And say I can do another picture. If I do that in gray, say. And then draw that tangent line. That's going to be even closer because the actual 0, if I draw it in purple, the actual 0 was right in here in the middle. So I've got x1, x2, x3, and then remember x4 here is this guy right here, this gray one here. So they keep getting closer and closer to it. You see how that works? Now, how in the world are you supposed to do that? But, well, let's go back to the very first one. Let's write the equation for the red tangent line. Any tangent line is y minus y1 equals m times x minus x sub 1, right? Where x sub 1, y sub 1 is a point on the line, m is a slope. Well, here's my point. So it's y minus, oops, I forgot a parentheses there, f of x1 equals the slope. The slope of the red line, that's just the derivative at that point. F prime of x sub 1 times x minus x1. Okay? Now, I want to know, what I'm trying to figure out is, what is this 0 right here? When I want to let y equal 0. Okay? So when y is 0, I get negative f of x1 equals f prime of x1 times x minus x1. And if I solve for x, I'm going to divide by f prime, f of x1 over f prime of x1 equals x minus x1, and I add x1 to the other side. So I get x1 minus f of x1 over f prime of x1. Okay, and because this is such a big deal, I'm going to change colors, and purple is kind of a cool color. So I get x, which is the x-intercept, which is x for my red line, which is x sub 2. Remember, this is the x-intercept. So that's x sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. Okay, so if I want to find the second, my second approximation, that's this guy right here. And it's all based on the first guess. So x sub 1 is my first guess. This is my second guess. Once you know the second guess, it's the same process. Because look, here's the second guess. I'm looking at the picture here. I find this point here, and I find my green tangent line and just do exactly the same thing. The nice thing is, I don't have to go back and redo everything. I know that my third approximation will be x sub 2 minus f of x sub 2 over f prime of x sub 2. And my fourth approximation is x sub 3 minus f of x sub 3 over f prime of x sub 3. And my fifth approximation, and so forth. Now the really nice thing about this is you don't have to go very far before these numbers get really, really close together. Okay, because as you can see, I go x1, x2, this purple dot in the middle is the real 0. These, the purple, the red, the green, the gray, they're getting closer, they're converging onto this purple dot right in the middle. Okay, really fast. So I just have to keep using this formula right here. Okay, I mean this series of formulas, it's the same formula just repeating itself over and over again until I get close enough as to however accurate I want to get. And that's what you were doing in your math class last year, is you would put a formula like this in your calculator and you just keep putting enter, and it would store it and then repeat it until it didn't change, and that just meant it got as accurate as your calculator could do it, which is like to so many decimal places. Okay, but I know that's not what the instructor wants now, because she wants you to be able to understand this more and just to work it out. So let's do an example, and I think that'll help you see it more. So let's take a look at this example here. I've got numbers already done here for you. So let's the question is this: let's make this thicker. Use Newton's method to solve x cubed plus 3x plus 1 equals 0, or that'd be the same thing as saying find the zeros for y equals x cubed plus 3x plus 1. I know I didn't need to say that, because I know you know that's the same thing. Keep making this thicker. Okay, so let's do that. Well, what do we need to know to do that? I'm going to write my formula down here, over here on the side. I know my formula is x, well, x sub 2 is, I'm looking up here now. Actually, let me come back up here. Let's generalize this. Notice x sub 2 is x sub 1, f of x minus f of x1 over f prime of x sub 1. x3 is x sub 2 minus f of x sub 2 over f prime. Right? This is always the next term. This is the previous one, right? So, in general, x sub n plus 1, that's the term after x sub n, because n plus 1 is after n, is the term right before it, n minus f of x sub n over f prime of x sub n. Okay, so if n is 3, this is 4. If n is 2, this is 3. Does that make sense? So there's my general formula. Okay, so we're going to use that now to solve this, and I'm going to go ahead and rewrite it up here. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. Okay, so I want to solve this, and I'm going to go ahead and figure everything out here. So I'm going to say this is, and there's different ways to do this. It depends if she wants you to make a table or whatnot. I think I'm going to go ahead and just fill this in so you can kind of see what's going on here. Let's go ahead and say, okay, f of x sub n is this guy, x sub n to the third plus 3x sub n plus 1. F prime of x sub n is simply the derivative evaluated at x sub n. So remember, y prime is 3x squared plus 3, so it's 3x sub n squared plus 3. So my nth plus 1 term for my Newton's method is x sub n minus, oh look, that's a text from you. Oops. Minus f of x sub n, I'm just plugging into this formula up here, x sub n to the third plus 3x sub n plus 1 over 3x sub n squared plus 3. And now this is my formula, so I can find my whatever my first guess is. I have to make an approximation for my first zero, and then from there I plug the first zero approximation in for x sub n, That's my n when n is 1, and then that'll give me 2. So I need to find x sub 1. So my first estimate for a0 is x sub 1. Now how do you determine what that should be? Well, the only way you can make a good, reasonable first estimate is to actually graph this on your calculator and just look at it, or have a picture of it or know what it is. And if you actually graph this on your calculator, it looks something sort of like this. Okay, where this is -1. So that looks like about, I'm going to say we're going to use -0.3. Okay, so let's do x1 equals -0.3. So that means this is, if n is 1, this is x sub 1 plus 1, or x sub 2, equals -0.3 minus -0.3 cubed plus 3 times -0.3 plus 1 over 3 times -0.3. I'm not a big fan of making tables. I just soon do it like this so you can see what you're doing. Equals. So if you do that, you get -0.322324159. You'll see why I'm carrying it out so far. X sub 3 is x sub 2. So it's going to be this guy. Remember, this is x sub 2. That's got to be in your calculator. You're going to have to store it into, A or something like that into your calculator, and then just put that A, just put that into your calculator here, or into your formula, but with A into each of those places. And I hope you know how to do that. If not, give me a call. And if you do that, you get point, and you should actually try this problem on your own to make sure you get these numbers: 3.221853603, x sub 4 -0.32218535546. So the question is, how long do you keep going for? Well, it depends how accurate you want to be. See, we're the same all the way out to 1, 2, 3, 4, 5, 6, 7 decimal places. And if your calculator only goes to 7 decimal places, they're equal. So depending on how far out, if they say we want it accurate to 3 decimal places, then you're accurate to this third place. The x sub 3 is accuracy to be 4. So it all depends how accurate you need to be. So it all depends on what your instructor wants on that one. Okay, so this is a pretty darn good approximation, and I think if you keep on going on your calculator, it's probably going to stay the same as this. I think if you do x5, in fact, it'll stay the same. So this is as close as our calculator will predict. Okay, and I'm just kind of looking at this, see in your book, looking at this example here, just so you can see this this example where Newton's method fails. But this is the example. Here's the formula right here. This is them plugging in the equation into the actual function right here into it. This is your f of x and your f prime, and so this is x sub 1, x sub 2, x sub 3, and they just did it in steps. Here's x sub n, f of x sub n, f prime, and then they divided it and then they subtracted it to get each one of these. Okay, so then you can compare and see, oh look, these two are exactly the same, so we can stop. Okay, and see, this tells you how far out to go. when you subtract the last two and they differ by less than 0.0001, then you're good, because that's how far they told us to be accurate, right up here. Okay. All right. So, buddy, I hope that So I hope that helps. I hope I didn't make it worse for you. But anyway, give me a call if you need more, or if you need more clarification or anything like that. All right. Thanks, man. I'll post this and give you a call.